The process of developing customized software, as we have seen, can be divided into 7 distinct stages: problem or need definition, system analysis, system design, programming analysis, program preparation, program implementation, and software maintenance. The first 3 steps come under the purview of system analysis and design. In this chapter, we concern ourselves with the last 4 steps, which deal with actual program development. We will study the various programming practices and languages that are used in creating customized software, as well as the process of maintaining software. Irrespective of whether one is designing a customized solution for an organization or personal application, designers and programmers usually have the same goals in mind. Goal 1, to address the user's specific needs. Goal 2, to develop and implement programs within a limited time and budget. Goal 3, to program the solution with a minimum amount of errors. Goal 4, to create programs that are easy to implement, use and maintain. In trying to achieve one goal, programmers are often faced with situations where trade-offs have to be made, such as, does one reduce the time allocated to the analysis and design stage and run the risk of creating potentially erroneous programs that may be difficult to maintain? Given the time, which method should one use? Does one create software from scratch, or should it be offloaded to another vendor on contract to adapt a ready-made package to one's needs? Programming a solution till this day remains an art, because people with similar problems can adopt many different views in answering these queries. As they say, there are many roads that lead to Rome. In trying to achieve the 4 goals, the world of software development has developed different program analysis and construction techniques. While each seems distinct, different organizations often use a varying mix of the following practices: program analysis approach, modular or top-down program design, the use of basic coding structures. Programming is the process of converting the system specifications created in the system analysis and design stage into machine-recognizable instructions to produce the desired result. During the programming analysis stage, the programmers must be able to arrive at a definite yes to essential queries such as, is the problem specification clear, concise and complete? Is he conversant with the solution method to be used? In the absence of a known method, can he locate a suitable solution from other programmers or journals or technical books? In the absence of any source of ready solutions, can he devise a solution from scratch? Programmers can use any one of the several programming analysis tools available. By far the most commonly used one is the program flowchart, a program code-based diagrammatic representation of the system flowchart. If the programmer opts for developing a procedure on his own, he often adopts the modular approach. This is a top-down approach in which the programmer breaks the solution into distinct smaller modules that are easier to solve. In this method, a main control program is devised to outline the major segments or modules that are needed to solve the problem. Typically, in a modular approach, the main control program supervises the entire process and has instructions that branch into the smaller module programs called subroutines at the appropriate time. The programming analysis process will continue till the programmer is convinced that each small module's solution has been clearly defined. The modular approach has many advantages. Complex and large programs are effectively broken down into smaller, simpler and more manageable modules. The smaller modules, being distinct in themselves, can be simultaneously coded by several programmers. One can then create a library of the module program. Program errors are more easily traced to a particular module, thereby simplifying the process of debugging and maintenance. One can effectively use tested subroutines prepared by software suppliers. The use of basic coding structures evolved out of the disadvantages of people-dependent programs of the yesteryear. Although the earlier programs worked, They used to be large with many complex branches. Understanding of codes, the branches, and logic by other people debugging and maintaining the system was a virtual nightmare. The late 1960s saw the emergence of the structured programming approach. This approach allowed any problem, no matter how complex or large, to be broken down into three standard logic patterns. The simple sequence structure, where one instruction follows another in direct sequence. The selection structure, where some condition is tested and is followed by two alternative control paths. If condition test, then control path 1, else control path 2. The loop structure, where the same lines of instruction are executed more than once depending on whether a condition tests true. As soon as a test false, the program control comes out of the loop. Do while condition and do until condition. When programs are structured and modular techniques are used, programs can be read from top to bottom and are much easier to understand. Structured programming techniques often include a peer review called a structured walkthrough during program construction to detect software errors. These are typically informal, relaxed sessions and are attended by a handful of programmers at the same level, no managers. In a structured walkthrough, one programmer will walk through his program solution step by step to show how it works, while the others review it and keep records of any errors that are apparent. The possible advantages of the peer review technique are: least amount of errors are likely to go through unnoticed, better program documentation can be made, program maintenance efforts become easier. The spirit of peer group cooperation results in higher programmer morale, speedier implementation, reduced development costs, and greater user satisfaction can be achieved. The ultimate goal of any program preparation effort should be to develop an effective product at an economical price. Having studied the programming methods and practices, let us now take a look at the organizational structure of a programming team. There are many ways in which the programming team is organized, although one cannot clearly opt for any one organizing practice and claim that it is the best approach. By and large, there appear to be three organizing practices, and organizations typically combine some of the features of these. Traditional hierarchical grouping, where a group of individual programmers is headed and controlled by a programming manager who may not actually be involved in the coding. Chief programmer teams, where the team comprises a chief programmer who is responsible for the project and actual coding, a backup programmer who assists the chief, may take on his role at any time and also develops important modules, a librarian who gathers and organizes all the records and documentation, and application programmers who do the actual coding as per the chief programmer's design. Ego-less programming teams, where there is no designated chief, but modules are assigned in a democratic manner to the most suitable person based on experience. Typically, these teams have peer reviews and the completed task is then the responsibility of the whole team and not a single person. Communication is possible only through the common medium of language. In order to be understood, the two entities in the communication must use the same language. Any language, be it a spoken or written language or a sign language or even the Morse code, has a definite structure, symbols and rules of grammar. In the realm of computers, a programming language consists of all the symbols, characters and usage rules called syntax, which permit people to communicate their program instructions with the computer. While some programming languages are created to serve a special purpose, like programming a robot, others are more flexible, general-purpose tools that are suitable for varied applications. Irrespective of the field in which it is used, every programming language must have instructions that fall into the familiar functional categories of input-output instructions, text manipulation and calculation instructions, logic and comparison instructions, and storage retrieval instructions. The evolution of software development has seen the emergence of four kinds of programming languages: machine languages, assembly languages, higher level languages or HLLs, and fourth generation languages or 4GLs. While each of these languages has the same categories of instructions, each has its own distinct set of symbols, characters, and grammar rules, which is very different from the others. As one progresses from machine languages to 4GLs, one is increasingly moving towards more human intelligible forms of codes. The machine language form is the rawest and most machine intelligible form that is perhaps just a step away from the electrical pulses in the circuitry. It consists of strings of binary codes comprising the bits 0 and 1 and is the only one that the processor directly understands. Any instruction in machine language has two parts: operation code and operand. The first part, called operation code or opcode, is the command or operation that tells the computer what function to perform. Every computer has an opcode for each of its functions. The second part of the instructions, called operand, tells the computer where to find or store the data or other instructions that are to be manipulated. Different computers can handle different number of operands in an instruction. Some are single operand machines that typically handle just one operand in the instruction. Example, add 1036 would add the value stored in address location 1036 to the ALU. Others are double operand machines that can handle two operands in the instruction. Example, add 1036 8656 would be interpreted as add the value in address location 8656 to the value in address location 1036. The actual machine language code for these examples would not have had any letters. In fact, the machine code for add 1036 might have looked like this: 00001, 0001, 00001, 00001, 000, 0011111, 0000. As a parent, coding and debugging programs in machine language was a tedious task that only specialized programmers could do. Further, in addition to remembering the dozens of code numbers for the commands in the machine instruction set, the programmer had to keep track of the storage locations of data and instructions. However, programs in machine language were executed the fastest since there is no time loss in translation. To simplify machine language complexities, developers devised the assembly language. In this language, mnemonic operation codes and symbolic addresses were used. The mnemonic codes were actual English letters that substituted the binary version of the operation code. Example, A for add, SIO for start input-output operation. The symbolic addresses allowed the programmer to express the address not in terms of its actual address location, but in terms of symbols that were convenient to the programmer. Since the codes now had human intelligible letters and symbols, the processing stage had to be preceded by a translation stage, wherein the mnemonics and symbols were converted into the machine code. The translation was handled by an assembly program or assembler. So, assembly language programs existed in two forms: source program, which was the program of instructions written by a programmer and could not be directly executed by the computer; object program, the machine code version that came out after the assembler had translated the source program, and this is what was actually executed. Assembly languages had a definite advantage over machine languages due to the following reasons. Coding was easier and faster since the language used had human intelligible codes. It reduced the time and minute detail involved in machine language coding. Errors were minimal, and those that did occur were easier to find. Codes were easier to modify than machine language programs. The biggest drawback of using assembly language was that they were machine dependent, that is, they were designed for a particular make and model of the processor. Both machine and assembly languages are often referred to as low-level languages. Since the objective of programmers is to make coding simpler, assembly language programmers devised improvements on the use of mnemonics by introducing macro instructions. These instructions were simple English-like codes. Example, write file, which refer to a series of previously prepared machine language instructions to perform the task. The development of mnemonic and macro instruction techniques paved the way for the development of high-level languages, also called HLL. Frankly, the reference to machine and assembly languages as low-level languages and the later human-oriented ones as high-level languages can be viewed as man's egotistical perception of viewing himself as a higher form of intelligence versus the dumb computing machine. Unlike assembly language programs, HLL programs may be used with different makes of computers with little modification. They also had the other advantages of being easier to learn since a lot of the syntax involved plain English, requiring lesser time to write, being able to generate better documentation, being easier to maintain, not being restricted to a single type of machine and processor. Like the assembly language, a HLL program also had two versions, that is, the source code or programmer's code and the object code or the translated machine code. A compiler did the task of translating a HLL program into the object code. In a compiler-based program execution, the whole source program is first translated and debugged into an object code, and then the whole object code is executed. Some high-level languages alternatively used an interpreter for translation, which is found wide use with personal computers. In an interpreter-based program, each source program statement is translated, debugged, and executed at a time. Since the object code in compiler-based programs is already debugged and in machine code form, they tend to execute faster than interpreter-based programs which do all three jobs instruction by instruction and can stop midway when an error is encountered. On the other hand, interpreter-based programs do not require a separate compilation process every time a program feature is added or modified. A further evolution of HLLs has led to numerous software vendors producing a variety of application development tools, often referred to as fourth-generation languages or 4GLs. The term fourth generation comes from the fact that some people consider the predominance of each language form as one generation. So, if machine languages were first-generation languages, assembly languages were of the second generation, HLLs of the third generation, and the later application development tools belong to the fourth generation. A 4GL tool interacts with the Database Management System or DBMS software to store, manipulate, and retrieve the data needed to satisfy user requirements. By their very structure and form, 4GLs are very easy to code and have a higher productivity. While the earlier generation languages were procedural languages, where each step in a procedure had to be spelled out, 4GL tools are non-procedural. They allow the user to simply specify what the output should be without describing all the details of how the data should be manipulated to derive the output. Generally, one cannot find a clear-cut distinction among 4GLs, although the following categories do allow us some form of categorization. End-users-oriented 4GLs, used for low data volumes by programmers or information users with their own internal DBMS that can interact with larger DBMSs and are easy to learn and use by people with minimum training. 4GLs oriented to specific DBMS packages, used for high-volume applications, have a detailed set of commands and require specialists to program solutions for desired output. Having studied the evolution and forms of programming languages, let us now look at some of the predominant high-level languages used in programming solutions. BASIC, or Beginner's All-Purpose Symbolic Instruction Code, is a popular interactive language that has wide appeal because it is easy to use. BASIC shot to popularity in 1974 when Bill Gates and Paul Allen devised a translating program for it for the Intel processor. The company, Microsoft Corporation, was initially formed to market this Gates-Allen version of BASIC and is now the leading software vendor in the world. BASIC is a very simple English-like coding language that can be learned and used by non-specialist computer operators. Due to its simplicity, it was first pushed into the PC market, where it gained tremendous success and today is by far the most popular high-level language used on PC systems. Entering data in BASIC is easy, and the problem solver need not be confused about the output formats because the usable format may be automatically provided. It is also easy to insert changes and allows very effective graphical capabilities. The flexibility and ease of use has made BASIC popular amongst people in various areas of application: school students, aerospace engineers, business managers, and recreational and educational software developers. Here is a sample of a simple basic language program. The origin of FORTRAN, or Formula Translator, dates back as far as 1954, when an IBM-sponsored committee headed by John Backus began work on a scientific mathematical language. 3 years of effort resulted in the birth of FORTRAN, which was developed for the IBM 704 computer. FORTRAN's strength lies in the ease with which it can express mathematical equations and its simplicity of structure. It enjoyed wide acceptance and was revised many times. In fact, many of its structures were later incorporated in the development of BASIC. FORTRAN is a compiler-based program comprising a series of statements that provide input-output, calculation, logic, comparison, and other basic instructions to the computer. FORTRAN was available in 2 standards, a basic or minimal version and a full or extended version, which was approved by the ANSI body. It is a compact language that serves the needs of scientists and business statisticians with extensive libraries of engineering and scientific programs. FORTRAN may be used for business applications that don't require the manipulation of extensive data files. FORTRAN was not very suitable for processing large business files. It was around 1960 that COBOL, or Common Business-Oriented Language, was developed for business data processing needs and till today remains the most widely used language for large business applications. COBOL is basically a compiler-based language that has over the years been developed for virtually all the processors used in business data processing. Today, they are also available for use with personal computers. The strength of COBOL is in its highly structured language format, where sentences direct the processor in performing the necessary operations. Related sentences dealing with the same operation are grouped to form a paragraph, while related paragraphs are grouped into sections, and these sections are further grouped into 4 divisions. The structural hierarchy of any COBOL program is completed by the following 4 divisions: Identification division, Environment division, Data division, and Procedure division. The use of case English terms that include commonly used business terms makes it easier for COBOL to manipulate alphabetic characters than FORTRAN. Over the years, a large library of business applications, modules, and programs have been developed by software vendors, including a COBOL generator, which draws on these libraries to automatically produce about 80% of the code in a program. However, COBOL is not a compact language and is not the easiest HLL programming language for most of us to learn. It is also not suited for complex mathematical calculations like FORTRAN. The limitations of FORTRAN and COBOL, being useful only in restricted areas of application, led groups of researchers to try and develop a universal language. Thus, PL1, or Programming Language 1, was implemented in the mid-60s to solve all types of business and scientific problems. PL1 ended up being a very sophisticated and flexible language that incorporated features from both COBOL and FORTRAN. It has a modular structure with related statements for an operation being combined into procedures, and these procedures could be independent small programs or modules of more complex programs. PL1 is a compiler-based programming language with a built-in feature called default options that can detect and correct common programming errors. A novice programmer may only learn a small part of the PL1 language in order to prepare application programs of a certain type. However, it is more difficult to learn in its entire form than either COBOL or FORTRAN. While COBOL found acceptance in large business applications, RPG or Report Program Generator was introduced in the 1960s primarily to process business applications on small business computers. As the name suggests, RPG was designed to basically generate output reports, but it could also handle input, calculations, and file updation. It was a limited purpose language because object programs generated by the RPG compiler follow a basic processing cycle without deviation. Since the program logic is fixed, there were fewer program rules to remember than with many other languages, and hence it was relatively easy to learn. RPG was well suited for applications where large files were read, requiring few uncomplicated calculations and standard output reports were used. Having restricted mathematical capability, it was not suited for scientific application. Another programming language that was developed for scientific and mathematical applications was ALGOL, or Algorithmic Language. It was introduced in 1958 by the efforts of an international group of mathematicians in Europe and the United States, including John Backus of the FORTRAN fame. Several versions of the language were created, the latest version being ALGOL 68. Like Pascal, it was a block-structured or modular language that enjoyed more popularity in Europe than the US. Another programming language that was developed for use in file processing in scientific applications was Pascal. As an offshoot from ALGOL, Pascal was the first major language to be created after the concepts associated with structured programming became widely disseminated. In Pascal, all variables are identified at the beginning of the program, and the instruction statements proceed in a logical flow that start with begin and terminate with end. A cousin of ALGOL and Pascal is the programming language ADA. Sponsored by the US Department of Defense, or DoD, ADA was developed for use by the military services and became an ANSI standard language in 1983. Though many find it unwieldy and inadequate, yet others labeled it as a breakthrough in software technology. The language will continue to exist since the US Department of Defense will require military computers to have ADA capability. You may be aware of the world-famous operating system called Unix. This Unix OS was coded in a special language that has tremendous capabilities called C. Over the years, it has developed into a general-purpose yet flexible high-level language. While it allows programmers to develop varied applications, it also allows specialist programmers to write programs in low-level machine instructions that are as complex and efficient as a machine or assembly language program. Today, the C compiler is bundled and marketed together with a Unix operating system and can be used on any machine architecture without much difficulty. C programming can use modular or structured concepts and has an extensive library of functions that are equivalent to subroutines. Any C program may be broken down into smaller tasks wherein a function may be used to solve each task, and the C program may become a grouping of functions that are linked together to produce the problem solution. Away from the world of business and science, we see the development of a language that has found great popularity as the first educational language, Logo. Logo's structure and easy-to-learn graphic features ensured that children could use it to achieve intellectual growth and develop problem-solving skills. Images are created by writing simple programs to move the drawing tool or the logo turtle on the display screen. However, the potential of logo goes beyond turtles and drawing. It runs on a PC and is also used in elementary grades and college classes to manage data, compose music, and manipulate text. Over the years, many other programming languages have been developed, some of which are APL, a programming language, an interpreter-based language for PC and larger systems capable of performing complex ALU operations with a single command. APT, or automatically programmed tooling, used to control machine tools in manufacturing applications. Fourth, somewhat like C, is a high-level assembly language used primarily by specialist programmers for in-house software projects and astronomical telescopic operations in observatories. Lisp programming language, has great strengths in its ability to manipulate non-numeric data and is extensively used in the fields of artificial intelligence. Modular 2, a more powerful and easier to use version of the original PASCAL language. Pilot, or programmed inquiry learning or teaching, an effective tool for computer-aided instruction material with programs that use drills, tests, and dialogues. Prolog, another sophisticated language that is used in the field of artificial intelligence and the main software being explored for fifth-generation computers. Snowball, or string-oriented symbolic language, a text manipulation and information retrieval language that is popular in the field of humanities. Programmers have access to this vast array of programming languages for writing instructions to control the computer operations while processing an application. However, the right choice has to be made before one begins the stage of program coding. Some issues that may concern programmers in choosing one language over the other can be solved by trying to answer the following questions. Is the programming team familiar with the language? Will the potential of the language support the nature of the application? Does the language support a modular structured programming approach? Does the language have efficient translating software, compiler or interpreter? How often will the application be processed? Frequently run applications would do better with assembly language programs which would execute faster and hence save on processor time. Will the program be changed frequently? An HLL program would be easier to modify and maintain. Is a hardware change anticipated during the life of the application? If so, a machine or assembly language program may not be the right choice since they are machine and processor dependent and may have to be rewritten. Is the language being supported, improved and updated? Enough resources should be committed to ensure that revisions and enhancements on the language continue and that it can be ported across any system. Once the language has been selected and the code written to completion, the next stage of developing customized software is implementation. Implementation involves executing the program many times with sample and real data so that errors, if any, can be fixed till satisfactory results are obtained. Often, the time and effort for these activities is governed by which practices were used during the system or program development stages. That is, tested pre-written packages, modular system or program design to divide the complex problems into more manageable units may make it easier to trace errors and to insert tested and proven subroutine modules as needed. Simple coding structures for easy maintenance, peer reviews and structured walkthroughs that result in fewer errors, faster testing, better documentation and easier maintenance. Bugs or errors arise due to typing mistakes and errors within the program itself. These bugs somehow occur even in the best of circumstances, and the time spent in debugging and testing often exceeds the time spent in coding. Program implementation can be broken into 4 steps. Executing the complete program to see that all the independent modules linked to the main program are working properly. debugging the program to detect and correct errors that prevent the program from running, testing the results to ensure that the input test data produces the predicted result, creating the complete documentation package to collect, organize, store and otherwise maintain on paper a complete record of why the application was developed, for whom, what function it performs, and how the application tasks are carried out. There are various items developed for testing the results. Typical data, which will test the generally used program parts. Valid but unusual data, which will test the program parts used to handle exceptions. Incorrect, incomplete, inappropriate data, which will test the program error handling capabilities. A number of pre-written packages are available to help people carry out their functions. Finally, the complete documentation package for customized software also follows a structure and must include the following sections: definition of the problem, objectives of the problem, for whom and under whose approval it was developed, description of the system, system specifications regarding scope of the problem, form and type of input, form and type of output, description of the program or programs, flowcharts, program listings, test data, test results with a historical record of difficulties and changes, recitation of operator instructions, detailed instructions for installing, running, operating, terminating and uninstalling the program, description of program controls, details of any special controls that were employed to ensure the reasonableness and accuracy of input data. Changes in operating environment or change in user needs can require existing systems to be modified or updated. This task of ensuring that the system results are always abreast with current needs is the job of the software maintenance team. Program maintenance is a more important task than developing the system, since it is a continuing activity that takes time and costs money. Here is a pyramidal representation of the cost involved in the program life cycle. Many organizations try and reduce this cost by using pre-written software that can automatically run through the program and identify areas of errors, change or updation. If the changes require the existing system to be completely revamped, then the entire process, right from the stage of system analysis and design, would have to be repeated.